Hi. This work gives tighter approximations of privacy loss distributions useful for privacy accounting of differentially private mechanisms. I am Pritish and this is joint work with Vadym, Badih, Ravi and Pasin. Differential privacy has become the de facto standard definition of privacy. A mechanism satisfies epsilon delta dp if for all neighboring datasets x and x prime, namely those which differ on only one input, it should hold that the probability of any event on input x is at most e to the epsilon times the probability of the same event on input x prime up to an additive delta. A motivating example to keep in mind is the DPSGD algorithm, which is a stochastic gradient descent algorithm where we add Gaussian noise to many batch gradient averages at each step. DPSGD has been quite popular for differentially private training of neural networks, for example. For any mechanism M and an epsilon value, the goal of privacy accounting is to compute a delta such that M satisfies epsilon delta dp. Accounting methods are essential for computing parameters underlying the mechanism, such as the noise scale in DPSGD. Here, I would like to give a shout out to the Google DP library, which we are actively developing. It contains privacy accounting tools among other algorithms. Now, there is a twofold goal when designing an accounting method. Namely, we want the computed delta value to be as tight as possible, and we want the computation to be as fast as possible. Privacy loss distributions, or PLD for short, provide a tight numerical approach to privacy accounting. At a high level, this approach works by associating a worst case or a dominating pair of probability distributions, P and Q, to a given mechanism, such that the e to the epsilon hockey stick divergence between P and Q gives an upper bound on the delta value of the mechanism for any given epsilon. This can also be naturally expressed in terms of the corresponding PLD. We will abuse notation to call this the hockey stick divergence of the PLD itself. The key property of PLDs that make them useful is that compositions of mechanisms simply corresponds to addition of the corresponding PLD random variables, or equivalently the convolution of the privacy loss distributions. For example, the PLD corresponding to the Gaussian mechanism is a Gaussian distribution. And so the PLD corresponding to self-compositions of the Gaussian mechanism is also a Gaussian distribution with a larger mean and variance. Thus, the goal of privacy accounting of composed mechanisms is reduced to the task of performing convolutions of privacy loss distributions. In order to make this practical, it is common to work with a discretized version of the privacy loss distribution. And furthermore, it is possible to perform the convolution operation in time that is nearly linear in the number of buckets using fast Fourier transform. In our work, we revisit the procedure of truncation and discretization introduced in prior work. And our main contribution is a new discretization procedure that provides tighter approximations to the privacy loss distribution for the purposes of estimating the hockey stick divergence. In order to describe our contribution, let's first revisit how discretization is done in literature currently. We start with a set of epsilon values that we want the discretized PLD to be supported on. We take epsilon 0 to be minus infinity and the largest epsilon value, namely epsilon k, to be plus infinity. To get a discretized PLD, one simply rounds up the probability mass in each bucket. This ensures that we get an upper bound, or what we call a pessimistic estimate, of the hockey stick divergence even after convolution with any other PLD. This approach can also be used to get a lower bound, or what we call an optimistic estimate of the hockey stick divergence, by simply rounding down the probability masses. One technical point to note here is that this optimistic discretization might not be a PLD corresponding to any pair of distributions, but it suffices to give us optimistic estimates of the hockey stick divergence. There is a lot more prior work on this topic, which differ in the details of the discretization procedures. But One thing common among all these approaches is that they all work by discretizing the privacy loss distribution directly. We use a fundamentally different approach in our work. In particular, instead of directly working with the privacy loss distribution, we work with a reparameterization of it, which let us call as the hockey stick curve. Our main technique then is to discretize the hockey stick curve using the approach we call as connect the dots. This approach works in such a way that when converted back into a PLD, it is discrete and precisely supported on the desired set of epsilon values. This approach can be done in both a pessimistic and an optimistic manner. I will describe our approach in this talk, starting with how to translate back and forth between privacy loss distributions and hockey stick curves. For any given PLD, its corresponding hockey stick curve is a function h such that h of e to the epsilon is the e to the epsilon hockey stick divergence of the PLD. This is simply a reparameterization of the delta for epsilon function. In a recent work, Zhu et al. Showed that a hockey stick curve corresponds to some PLD if and only if it satisfies certain properties, namely that it is convex, non-increasing, h of 0 is 1, and h of alpha is at least 1 minus alpha. We build on this result and show that a hockey stick curve corresponds to a discrete PLD supported on a given set of epsilon values if and only if the same properties hold in addition to two more properties, namely that the curve is piecewise linear, with the anchors being the e to the epsilon values, and moreover the curve is a constant for all values greater than the last finite e to the epsilon value, which is e to the epsilon k minus 1. When these properties hold, we show how to reconstruct the corresponding discrete PLD efficiently and in a numerically stable manner. This completes the translation between privacy loss distributions and hockey stick curves. Finally, I will describe the approach of connect the dots to discretize a hockey stick curve. In order to do that, it is important to note a key theorem shown by Zhu et al. That if we have two hockey stick curves, h1 and h2, such that h1 is always less than or equal to h2, then the PLD corresponding to h2 gives rise to a pessimistic estimate of the hockey stick divergence over the PLD corresponding to h1. Thus, given any hockey stick curve and a specified set of epsilon values, we have a natural approach. We simply connect the dots to get a piecewise linear hockey stick curve that is precisely anchored on the desired e to the epsilon values, thus corresponding to a pessimistic PLD that is discrete and supported on precisely the specified set of epsilons. In fact, this construction is the tightest possible pessimistic PLD that one could get that is supported on the given epsilons. For example, this can be seen by comparing to the hockey stick curve attained by the prior approach I described earlier of rounding up probability masses. We also provide an algorithm to get an optimistic PLD that is based on a greedy algorithm to choose a candidate set of points that the curve would be anchored on, and then using a convex algorithm to find a subset of the anchors that form the optimistic hockey stick curve. It turns out that unlike the pessimistic hockey stick curve, there is in fact no unique best optimistic choice. Our algorithm is just one of the choices that we found to be giving good optimistic estimates empirically. Our algorithm shows a significant improvement over the implementations available in the current Google's Differential Privacy library and Microsoft's PRV accountant. These plots show a comparison between our new algorithm and these implementations using the same set of epsilons given to each algorithm. Our algorithm thus gets a significantly tighter estimate of the privacy parameters for roughly the same computational running time. For more details, please see our paper. To summarize, our new approach of connecting the dots can provide tighter discrete approximations of privacy loss distributions, which provides superior approximations compared to prior work at the same level of discretization. Some potential future directions on this work include theoretically understanding the error guarantees of our approach, as well as investigating other approaches to obtaining optimistic discrete PLD. For more details, please see our paper or visit us at our poster. Thank you.